Okay, so this is going to be a fairly quick talk because we had some miscommunication on my end of things, and I wanted to reveal some things to you that I can't reveal. So instead of having a bunch of simulation results and things like that, we're just going to talk about a couple things we've been talking about building into MarFS at a couple different levels. So I don't think anyone's going to hear anything surprising here in terms of drive. Do we have to worry about that alarm that's going off outside? Okay. Yeah. Okay, so moving on. I'm going to be talking about just the types of different drive failures that people typically see in practice, and I don't think that's going to be news to anyone. But I just wanted to put it down on paper and start a discussion about it. And for the reasons that we are moving away from flat erasure or RAID schemes, or parity schemes, because there are various things that can happen at scale that don't really matter on a small scale or medium-sized scale, but when you start pushing 10, 20, 30,000 drives, some of the basic math breaks down at that point. So everyone knows random drive failure. I mean, things break. Most systems these days handle the random drive failures fairly well. It's not really something that there's a whole lot of inroads on anymore. Distributed rebuild, takes care of the random failures, even if they happen fairly quickly. And if the drive's getting larger and larger, that's somewhat helpful. You get a balancing problem down the road with distributed rebuild, but it's not the end of the world. It's just a performance deficit for a few hours or potentially a couple days while you're rebuilding a 12 terabyte hard drive. But this is a solved problem, I would claim, at this point. One of the things that does drive everyone bonkers when you're a sysadmin is correlated drive failure. So when you have a bad firmware, when you have an electrical event, when somebody knocks your rack over, which hopefully doesn't happen very often, but I've seen it, and a whole bunch of drives in one specific area break. And this is correlated in space for those particular kinds of failures. So they're all fairly local within a small area. So if you have multiple data centers, you can spread your data out. That's no problem anymore. But some people only have one data center, or they have one large data center with all the stuff kind of in the same area. But at least for correlated failures in space where they're all within a rack or within a server, that's fairly easy to avoid if you're clever with how you place your data. And correlated in time is another thing that those are hard, where you have an entire system that has an event, and that event doesn't affect a rack, it doesn't affect a server, it is 50 or 100 drives across the entire campus or more, and there's no real rhyme or reason to which ones die. And that's one of the things that isn't really solved with standard placement algorithms in both current RAID and distributed file systems, as well as cloud storage systems that tend to use a hashing algorithm to pick where the chunks of an object go. So say you're doing erasure of 20 plus 4, and I used this example yesterday, is that if you have 5 drives simultaneously die in the system and you have a system that's fairly full, you have probably lost an object, and that probability approaches 1 with the more objects you have in the system, because the likelihood of having a stripe line up with the 5 drives that failed approaches 1. And this is the one that I didn't even like writing it down, because no one can fix it. If you have a firmware failure that takes out 50% of your drives in the span of a day or two, there's nothing you can do. I just stuck it in here because if I was talking about types of drive failures, there is always the horror case of everything's dying because something broke, or you had a power spike that killed everything all at the same time. And some people can afford to replicate across multiple sites to avoid this, or buy from enough vendors that it's not a problem. But when I'm chasing the 4 and change cents per gigabyte storage, we can't afford to do replication to fix this problem. So basically, you give up if something like this happens. At least that's my perspective. So this is the typical set, is you have +2, +3 for RAID protection, and this is old hat these days. But as you scale large enough, every single thing, no matter how small the failure probability, if you have enough of them, you have a failure probability that's becoming significant. So I unfortunately have built a few systems in the past that fell prey to the, oh yeah, RAID 6 is great, except when you have 3 petabytes of small drives in RAID 6 sets, one of them failing takes out a huge chunk of your data, because typical big POSIX systems, you're striping. And there's not really much protection you can do beyond that besides replication. And then there's distributed erasure, which is this flat protection scheme where most erasured systems, at least for object or block even, have some placement algorithms that will break down if you have many, many thousands of drives and you've got some large number of instantaneous or fairly close to each other in terms of time drive failures. And you can combat this a little bit by, with my 20+4 example, you don't really put 20+4 and then place it across 30,000 drives. That's a good way to lose some data. But what you can do is chop it up and put it into smaller domains, but then you're losing some of the benefit of those placement algorithms in that you can spread your load over the entire system. Instead, you're spreading your load over some small set of it, potentially. So what we started to build, and what we have built within MarFS is a tiered concept. It's like the 2D, CERN has a 2D placement algorithm as well. It's basically the same thing. So as we build bigger and bigger systems, if you can tolerate the latency and you can tolerate the additional compute overhead of doing multiple tiers of erasure, you can get the benefit of the fast computation of those algorithms with small sets of plus parity. So if you say 10+2, 17+3 is much easier to calculate, for example, than 170+70, which is the equivalent of what it would be in our system if we had built out a flat scheme in terms of the cost of the overhead. And Intel guy in the audience, where were you at? Using ISAL, there's a couple of you, we benchmarked up to +70 erasure, and not only to give it gargantuan data blocks for it to even be remotely efficient, the bandwidth of being able to compute that approaches, I wouldn't say zero, but it's certainly, as you go from +2 to +3 to +4, you're losing bandwidth each time because it's more complex math. And out at +70, you sell a lot of Intel CPUs, but that's not the business that we're in. So we're trading off some things that fit our use case specifically, in that multiple tiers of parity give us the protection that some people are trying to call it an archive, and that we've said, yeah, our mean time to between data loss is going to be some gargantuan number unless we have a systemic drive problem. I don't like calling things archives when they're connected to the grid or anything like that. I don't even call it a backup if it's connected to the grid. It's just longer term storage that you can kind of ignore a little bit more. So it doesn't fit every case, but that's what we're doing to protect our data. And then here's the picture of the setup that we had from yesterday, that we just were building out a whole bunch of these sets of pools where we've got lots of storage nodes with independent failure domains, and then we're striping across the failure domains so that we can tolerate rack losses and server losses without too much heartache. But that's all I have for today. Any questions?
Thank you, David. Bummer, we didn't get the performance numbers, but that's okay. Next conference. So questions for David on what Los Alamos is doing with tiered erasure? Cool. Any questions? Okay. All right. Again, thanks.